Uh, Good evening to all. Welcome to the 11th week problem solving session of NPTEL course IC Engines and Gas Turbines. My name is Ananthakrishnan. I'm a Ph.D. student from IIT Delhi. Uh, I do this problem solving session for this NPTEL course as part of my PMRF TA duty. So in this week, the lecture contents available in the website, NPTEL website, where radial flow turbines, nozzles and diffusers of the engine, gas turbine, nozzles and diffuser for aircraft engines. So without wasting much time, we will move to the this week's problems. I'll give you 1 minute just to look into the problem and I'll try explaining this afterwards. So the question is regarding a single stage turbine of free vortex type, and the total head inlet pressure is 4.6 bar. Total head inlet temperature is 700 degrees Celsius. So that corresponds to the stagnation pressure and stagnation temperature respectively. Static head pressure at mean radius is 1.6 bar. Mean blade diameter per blade height. The ratio of the mean blade diameter to the blade height is given as 10. Nozzle loss coefficient is 0.1. Nozzle outlet angle is 60 degree. We have to determine the gas temperatures, velocities, and discharge angle at the blade root and the tip radii. So at two different points, we have to calculate the discharge angle at the blade root as well as the tip radii at the innermost point and at the outermost point. Cp is given as 1.147, gamma is 1.33, mass flow rate is 20 kilogram per second. We will try to represent the problem using velocity triangle. So In this particular problem, we will denote point 1, 2, 3 for entry to the nozzle, exit of the nozzle, that is the entry to the moving blade and exit from the moving blade. So 1 corresponds to entry to the nozzle. 2 corresponds to exit of the nozzle for the entry to the moving blade. 3 corresponds to exit from the moving blade. So T01 corresponds to the stagnation temperature after expansion. Or before expansion, I beg your pardon. Expansion. Let us draw the velocity triangle. So this will be the axial velocity term or the actual velocity. The actual velocity is vertical component CA. Actual velocity will be C1. So this is the inlet to the nozzle. It will be making an angle of alpha 1 and let V1 be the relative velocity. It will be making an angle of beta 1. Let U be the blade velocity. V1 will be the wall velocity or the horizontal component of the actual velocity term. So from this, we can calculate. We in the question it is mentioned that we have to calculate the gas temperatures, velocity, and discharge angle at the blade root and the tip radii. So in this given problem, T01 is given as 700 degrees Celsius. For an isentropic process, so isentropy, since it's a single stage turbine, for an isentropic expansion, we can relate between the isentropic temperatures as well as the pressures using the equation for the isentropic process. So using that, we'll get T2 dash divided by T01 equal to T2 dash is equal to P static at the mean radius divided by stagnation pressure divided by gamma minus gamma. From this equation, we'll get we can substitute the values of the unknowns. T2 dash divided by 973 is equal to P2 is given as static pressure at the mean radius 1.6 bar at the exit of the nozzle or the inlet to the moving blade. P01 is given as the stagnation pressure at the inlet as 4.6. Gamma is given as 1.33. So the value will come to be 0.77. Therefore, T2 dash or the isentropic temperature, static temperature at the exit of the nozzle can be written as 0.77 into 973. So it will be coming around 749.2 Kelvin. So in this given problem, nozzle loss coefficient is given as 0.1. So the formula for nozzle loss coefficient is in terms of enthalpy Cp into T2 minus T2 dash. That is the actual temperature at the static temperature at the exit minus isentropic static temperature at the exit of the nozzle divided by half into T2 squared. Therefore, from this one, we can write 0.1 equal to Cp into T2 minus T2 dash divided by half into C2 squared, denoted by equation 1. We do not know the actual velocity at the exit of the nozzle or at the inlet of the blade. We can calculate this in terms of the stagnation temperature difference, stagnation temperature minus the static temperature. So we can represent T02. We have calculated T2 dash from the previous analysis. And we know we have to calculate T02. T02 is equal to T2 plus C2 squared divided by 2 Cp. So the stagnation temperature at the exit of the nozzle can be written as static temperature plus the dynamic value of the temperature represented using C squared divided by 2 kinetic energy divided by Cp. That is from the equation of the stagnation temperature. So substituting C2 squared divided by 2 Cp using T02, we can get the 2 in 1. Point 1 equal to 0.1 equal to T2 minus T2 dash divided by T02 minus T2. So this nozzle loss coefficient can be represented in terms of the temperature difference between the isentropic and the actual values at the exit of the nozzle divided by the stagnation temperature minus static temperature at the exit of the nozzle. We know the value of T2 dash as 749.2. And T02, that is the stagnation temperature at the exit of the nozzle. Since this is a nozzle and there is no work production in the nozzle, we can write the stagnation temperature at the exit of the nozzle equal to the stagnation temperature at the inlet of the nozzle. So T02 equal to T01 equal to 973 we can write. So substituting this value, substituting this value 3 into we'll get 0.1 is equal to T2 minus T2. Solving for T2 we'll get T2 is equal to 769.5 Kelvin. So we have calculated the temperatures T2 dash and T2 as well as T02 value. Now we can calculate the velocity at the exit of the nozzle. T2 T2 squared divided by 2 is equal to Cp into using this equation T02 minus T2. So C2 is equal to root of 2 Cp T02 minus T2. So 2 into Cp is given as 1.147 kilojoule per kilogram Kelvin. So 1147 into T02 will be 973 minus T2 will be 769.5. So solving for this, we'll get the value of the velocity to be 623.525 meter per second. So we have calculated the velocity at the exit of the nozzle and the actual temperature static temperature value at the exit of the nozzle. Then we have the value of temperature and we have the value of the temperature and the velocity at the exit of the nozzle. Now the next step is we have to calculate the discharge angle at the blade root and the tip radii. For that, we should be knowing about the blade diameter values. How to get the blade diameter values. For that, we need to know the area as well as the mean diameter. So in this particular problem, the mean blade diameter divided by blade height is given as 10, and the nozzle outlet angle is given as 60 degree. So alpha 2 can be represented as 60 degree. So for this analysis, we can calculate. In this particular problem, the mass flow rate is given as 20 kilogram per second. So we know the mass flow rate. We can calculate the axial velocity and we can calculate the density. And from these three values, we can calculate, we can determine the value of area, and using the area, we can determine the value of the diameters, mean diameter, as well as the from the mean diameter to blade height ratio. We will try to do that in the next analysis. So the axial velocity CA2. So in this particular analysis, the axial velocity remains the same throughout. So CA1 will be equal to CA2 will be equal to CA3. CA2 is equal to from the velocity triangle CA2, that is a vertical component, can be written as P1. Beg your pardon. From a similar analysis, this is the inlet to the velocity inlet to the nozzle. At the exit of the nozzle, it can be written as C2 cos alpha. The nozzle outlet angle is given as 60 degree. So C2 cos alpha, C2 cos alpha 2. C2 is given as 683.25. We have calculated it. Cos of 60 is equal to 1/2. So we'll get it to be around 341.63 meter per second. So the axial velocity CA2 is equal to 341.63 meter per second. Sorry, meter per second. Then we can calculate the density ρ2 is given as P2 divided by RT2. The exit static pressure is given as 1.6 bar. So 1.6 into 10 power 5. R can be written as 284.6. And T2, the static temperature is equal to 769.5. we'll get the density to be equal to 0.73 kilogram per meter cube. Using density, axial velocity, and the mass flow rate. Mass flow rate is given us in this problem as 20 kilogram per second. So we can calculate mass flow rate is equal to rho 2, A2, and C2. So CA2. So that is from this we can calculate A2 is equal to 20 divided by 0.73 multiplied by 341.63, that equal to 0.08 meter squared. So after calculating this one, we can calculate the diameter values. We need to calculate, ultimately we need to calculate the angles, blade angles at the blade root, discharge angle at the blade root and the tip radii. So we can calculate, we know the ratio between the diameter to the height is given as 10. The mean blade diameter to blade height equal to 10. So mean blade diameter dm to blade height h is equal to 10. So area can be written as pi into diameter into height. For the axial mass flow rate, you can write it to be pi into diameter at the mean point multiplied by height. So height can be written as dm by 10. So we'll get dm squared is equal to 10a2 divided by pi. Therefore, dm is equal to root of this value 10 into 0.8, 0.08 divided by pi. So we'll be getting it around 0.5 meters. So the mean blade diameter equal to 50 centimeter. And the blade height equal to 50 by 10 equal to 5 centimeter. So we will be calculating the root as well as the tip diameter values at the root. Diameter of the root diameter diameter minus height. So that will be giving the diameter of the root, mean diameter minus height. So it will be 50 minus 45 centimeter. And at the tip, at the extreme point, at the outermost point, diameter tip is equal to dm plus h is equal to 55 centimeters. So in this particular problem, it's been mentioned that it's a free vortex type. It's a free vortex type single stage turbine. So the property associated with the free vortex type is that tangential velocity into r must be constant. So C omega at the tip into R tip should be equal to C omega at the mean point into R of mean point. So this value C omega of the mean point, mean diameter, the tangential velocity or the wall component of the velocity at the mean component is an unknown. So we can calculate the wall velocity at the unknown at the mean point using the value of the axial velocity and the blade angle, alpha blade angle at the inlet or the exit of the inlet of the blade or at the exit of the nozzle. So we can represent this by using equation 4. We know the value of R mean, R tip. So in order to calculate the wall velocity at the tip, you need the wall velocity at the mean point. So wall velocity at wall component of the velocity at the mean point will be given as C2 into sine alpha. The axial velocity component we have represented as C2 into cos alpha. C2 into cos alpha. So the wall component is represented C2 into sine alpha. So 683.25 into sine 60. So that will be coming around 591.71 meter per second. So we have calculated CW mean. Therefore, CW, the tangential velocity component at the tip is equal to CW mean into R mean divided by R tip. Mean component R mean radius of the mean radius will be equal to 25 centimeters, and the tip radius will be 27.5. So the axial velocity component, the wall velocity component at the tip will be equal to 537, slightly lower than the mean component in order to keep the free vortex criterion constant. Similarly, Similarly, at the root, CW root into R root equal to CW mean into R mean. So we can write CW root equal to CW mean into R mean divided by R root. So CW mean is 591.71 multiplied by 0.25 divided by 0.225, that is half of 45 centimeters. So it will be coming to be around 657.4 meter per second. So this will be equation number 6. We have calculated the whole component of the velocities at the root as well as the tip. Now we have to calculate the blade angles at the we have to calculate the blade angle at the inlet of the nozzle. Or the discharge angle. Blade angle is similar, is a different term for the discharge angle at the blade root and the tip radii. So we can calculate. I beg your pardon, we need not calculate the blade angle in this particular problem. The discharge angle, we have to calculate the discharge angle at the blade root and the tip radii. So we need not calculate blade angle in this problem. We have to calculate the same nozzle outlet angle or the inlet to the blade at the blade root and the tip. So that value will be slightly different from 60 degree. At the root, and at the blade, we have to calculate the discharge angle. So we have to calculate alpha 2. Alpha 2 at the root is equal to tan inverse of CW2 root divided by CA2. So CA remains a constant throughout for the axial turbines. Alpha 2 at blade tip will be equal to tan inverse of CW2 tip divided by CA2. So we have calculated the root tangential compound, world compound is equal to 657.45. And the axial component will be CA cos alpha. So that will be 341.663. Similarly, at the blade tip, it will be 537.9 divided by 341.63. So it will be coming around at the root, the angle alpha 2 will be coming around 62.5 degree, and at the tip the angle will be coming around 57.6 degree. So the discharge angle at the root will be slightly higher compared to that of the tip. The next one, we have to calculate the blade velocity and the static temperatures at these 2 points, at the root as well as the tip. The blade, the not blade velocity, the actual velocity. So C2 at the root will be equal to CA2 root divided by W2 root divided by sine alpha root, or you can write it to be CA root divided by cos alpha root. CA root will be same as that of CA blade tip. CA value will be constant divided by cos alpha value you can vary. So CW root will be equal to 657.41 divided by sine 62.5 degree. So that will be coming around 741.2 meter per second. And the C2 at tip will be equal to CW to tip divided by sine alpha at the tip. So that will be equal to 537.9 divided by sine 57.6. That will be coming around 637.1 meter per second. After calculating the velocities, we can calculate the static temperatures. Since it's a nozzle, the stagnation temperature remains throughout before and after the nozzle. So T2 can be written as T02 minus C2 squared root at the root divided by 2 Cp T2, the stagnation temperature, the static temperature at the root, static temperature at the root. Similarly, T2 tip can be written as T02 minus C2 squared tip divided by 2 Cp. So this will be coming around T02 will be 973 minus C2 root is equal to 741.2 square divided by 2 into 1147. It will be coming around 733.5 Kelvin. Similarly, here it will be 973 minus C2 square 637.1 square divided by 2 into 1147. It will be coming around 796 Kelvin. So we have calculated the static temperature, velocity, as well as the blade, the discharge angle at the nozzle exit or the inlet to the blade. So this was the problem which we have attended. In this problem, we have to calculate the gas temperatures, the velocity, and the discharge angle at the blade root and the tip radii. Initially, we have calculated the stagnation temperature. Since this is a nozzle and no work is produced in this one, we can calculate we can assume that the stagnation temperature at the inlet and the exit of the nozzle will remain the same. So in this particular problem, we have calculated the static isentropic value of the temperature at the exit, and using the nozzle loss coefficient, and equating the kinetic energy value to be equal to the enthalpy change, we can calculate the static temperature at the exit of the nozzle T2, and using the static temperature value and the stagnation temperature value, we can calculate the velocity, actual velocity at the exit of the nozzle C2 at the mean blade radius. This analysis, the initial analysis is done at the mean diameter of the blade, and therefore we can calculate the from this mean blade velocity, we can calculate the axial velocity, density, and from the mass flow rate, we can calculate we can determine the area at the mean diameter for the fluid flow, and using the mean blade diameter to the height ratio, we can calculate the mean blade diameter from this area value which you have obtained from the mass flow rate, and using the analysis, using further analysis, we can calculate the temperature, velocity, and the discharge angle at the blade tip as well as the blade root. So what we use is the free vortex criterion of tangential world component of the velocity multiplied by the radius at which it is considered will be a constant. Okay, so that completes the first problem. So second, we consider the degree of reaction of a reaction turbine is given by which formula? I'll give you a minute to look into it and I'll try to explain it. So the answer is The solution to this problem is B. Let us see how it is being done. The degree of reaction say turbine stage can be defined in more than one way. So using the isentropic change in the stage, we can express the degree of reaction as degree of reaction is denoted by letter R is equal to isentropic change of enthalpy in the rotor to isentropic change of enthalpy in the overall stage. So this can be represented as if one is the nozzle inlet, two is the nozzle exit, three is the blade exit. So two corresponds to blade inlet as well. We can represent it as we can represent this in terms of the enthalpy change, isentropic enthalpy change of the rotor, that is the blade, divided by the overall stage isentropic enthalpy change, H1 dash minus H3 dash. H1 need not, H1 is equal to H1 is. So H1 will be same as that of H1 dash. So it can be written as H1. Uh, so assuming a constant rho, the enthalpy change can be represented as delta P by rho. Hence, the degree of reaction can be also represented as the change in pressures P2 minus P3 divided by P1 minus P3. But the issue with these two reaction equations are that these are calculated based on the isentropic values, but we need to calculate it based on the actual enthalpy changes. The actual enthalpy changes in the rotor as well as the work are more important for turbine stages. So we represent these degree of reaction in terms of the actual enthalpy changes. So in the rotor, actual enthalpy change H2 minus H3 So we can represent the change of enthalpy through the rotor. We can represent the enthalpy change in the rotor as H2 minus H3 as a combination of the relative velocity kinetic energy changes as well as the tangential the blade velocity kinetic energy changes, and the total change in the enthalpy uh, for the stage is equal to H0 minus H01 minus H03. That is same as H02 minus H03 because there is no enthalpy change within the nozzle. Only in the rotor there will be enthalpy change. So it can be written as U2 CW2 minus U3 CW3. So the degree of reaction can be written as, so along with these R can be written as H2 minus H3 divided by H01 minus H03. So this is yet another equation. If we can assume that C1 is approximately equal to C3, then H01 minus H03 will be approximately equal to H1 minus H3. Therefore, degree of reaction can be written as H2 minus H3 divided by H1 minus H3. So this can also be written as, substituting the values, half into So this can be written as H2 minus H3 divided by H1 minus H3. can be written as half into so R, therefore R can be written as H2 minus H3 divided by H1 minus H3 equal to relative kinetic energy or relative velocity kinetic energies difference plus the blade velocity kinetic energy difference divided by the work overall work done in the stage H1 minus H3 for the work in this stage that will be equal to U2 CW2 from the Euler turbo machinery equation U3 CW3 the work done on the system. So U2 CW2 minus U3 CW3 for axial machines. We can write U3 equal to U2 equal to U. So we can take the U outside. Therefore, it will reduce to degree of reaction R is equal to the relative velocity at the exit of the rotor to the inlet of the rotor divided by 2U into CW CW2 minus CW3. So this can be expressed from velocity triangles. The relative velocity squared can be written as the axial velocity squared plus tangential component of the relative velocity squared. Similarly, V3 squared is equal to CA3 squared plus VT3 squared for constant axial velocity. We can write V3 squared minus V2 squared is equal to VT2 squared minus VT3 squared minus VT2 squared. So this quantity can be written in terms of the axial velocity component, axial velocity is a constant, CA2 into tan beta 3 squared minus tan squared beta 3 minus tan squared beta 2 Therefore, we can write from the equation from the equation 4. From the equation 4, we can write V3 squared V2 squared So we have got one equation of CA squared into tan squared beta squared minus tan squared beta 2 squared. So it can be written as CA squared into tan beta 3 plus tan beta 2 into tan beta 3 minus tan beta 2. So uh, CA into tan beta 3 minus tan beta 2 can be represented as CA into tan beta 3 plus tan beta 2 into CA into tan beta 3 minus tan beta 2. So this can be written as the in terms of the from the velocity triangle in terms of the tangential component of the tangential component of the relative velocity. So it can be written as VT3 plus VT2 into VT3 minus VT2. So we can represent omega 3 squared minus the relative velocity squared at the difference of the relative velocity squared at the exit of the blade and the inlet to the blade. Tan beta 3 minus tan beta 2 into CA into tan beta 3 plus tan beta 2 can be written as CA into the value of CA tan beta 3 plus tan beta 2 equal to the tangential component of the axial velocity. So it can be written as CW3 from equation 5 and equation 6 from 4 and 6. We can write this to be CW, beg your pardon, 7. This is equal to 7. So from from 4 and 7, CW3 plus CW2 into tan beta 3 minus beta 2. So So from equation 5 and 8, we'll get V3 squared minus V2 squared divided by 2U into CW plus C3, CW3. So substituting the value from 8, we can cancel out CW3 and CW2, the summation of the quantity. What remains is CA divided by 2U into tan beta 3 minus tan beta 2. So the value, we'll get it in the form of option B. So that completes the numericals for this session. Now we look into a few multiple choice questions for the nozzle, different types of nozzles and the diffusers. Uh, which statement is correct about the ramjet engine? Air enters the engine with subsonic speed and encounters subsonic combustion. Air enters the engine with subsonic speed and encounters supersonic combustion. Air enters the engine with a supersonic speed and encounters subsonic combustion. Air enters the engine with a supersonic speed and encounters subsonic combustion in the combustion chamber. So the answer is air enters the engine with a supersonic speed and encounters subsonic combustion in the combustion chamber. So if you try to draw the ramjet engine, So in the case of ramjet engine, there will be the air will be entering at supersonic speeds. This is the inlet ramming effect producing equipment. Ram. So the air will be incoming into the engine at Mach number greater than 1. So for supersonic speeds, so the inlet will be supersonic speed, but for a converging duct will be acting as a diffuser whose pressure increases instead of having uh, some rotating device or moving part like a compressor. This presence of the Mach number greater than 1 produces shock waves that will be producing compression to the air. So rather than a mechanical compression, it is a thermodynamic compression. And once it goes through the converging duct, its pressure increases and velocity decreases since this Mach number is greater than 1. And while reaching the lowermost point of the area before the combustion, at the most converged the choke area or the converged most the area with the least value, its Mach number will become less than 1 and it undergoes combustion. And then again its Mach number increases and the diverging part will be acting as a nozzle whose velocity which ensures that the Mach number at the exit will be greater than 1, producing greater thrust. So the advantage with this kind of ramjet engines is that it can get away with the moving parts like compressor and turbines. The shock waves itself produced inside the engine can be used for increasing and decreasing pressure as well as the velocities. So air enters the engine with supersonic speed. Its velocity decreases, Mach number reduces, and it encounters subsonic combustion. And again, the velocity increases. The nozzle will be the diverging part will be acting as a nozzle for the supersonic air which is coming out of the combustion. So here the Mach number will be greater than 1, and this will be acting as a nozzle. So the answer is air enters the engine with a supersonic speed and encounters subsonic combustion in the combustion chamber. The flow through the nozzle is said to be underexpanded when the nozzle exit pressure is higher than ambient pressure, equal to ambient pressure, equal to reservoir pressure, lower than the ambient pressure. So the correct answer is when the nozzle exit pressure is higher than the ambient pressure, the flow through the nozzle is said to be underexpanded. So the pressure at the inlet, the pressure at the inlet will be the reservoir pressure, decreases, and then again increases. So if the pressure so correspondingly there will be a P ambient pressure, there will be P reservoir pressure, and when the outlet pressure is less than the inner pressure, the flow occurs, and for Mach number less than 1, it reaches the throat, and from then onwards, for the diverging pressure, pressure increases to the exit. So till when the pressure is above the ambient pressure, the exit pressure is above the ambient pressure, the flow is said to be under expanded as the full utilization of the diffusion section, the diffuser part or the diverging part is not taken into account. Then once the throat area, the choke is achieved, when Mach number at the throat is equal to 1, then it starts increasing, and then the pressure will at the exit will be less than the ambient pressure, and in that case the section the flow is the nozzle exit pressure will be less than the ambient pressure, and then the flow is said to be flow through the nozzle is said to be over expanded. So when the pressure regime at the exit is greater than the ambient pressure, the complete expansion is not achieved, and the flow is said to be under expanded. So the answer to this problem is higher than the ambient pressure. Okay. For a given reservoir temperature and pressure, the flow at the minimum cross-section area of the choked convergent divergent duct nozzle should be subsonic, sonic, supersonic, or hypersonic. The throat area will be the choking area, and the given nozzle is a convergent divergent nozzle, and the choke flow. The mass flow rate keeps on increasing till the Mach number of the throat will be equal to 1. So the answer is sonic. For a convergent divergent nozzle, this is the minimum cross-sectional area point. This is the converging part, this is the diverging part, and this is the throat. So the Mach number when less than 1, the converging section will be acting as a nozzle, and then the diverging, if the Mach number at the throat is less than 1, the diverging section will be acting as a diffuser. But for Mach number greater than 1, Mach number greater than 1, a diffusing section will be acting as a nozzle, and a converging section will be acting as a diffuser where the pressure increases. And for Mach number less than 1, and if the mass flow rate increases such that the throat Mach number is equal to 1, and then it increases beyond that particular point, the shock waves created ensures that the diverging section will be acting as a nozzle, and at the end, the Mach number will be very much greater than 1. It keeps on increasing. So this is the advantage with the converging diverging duct. And for a given reservoir temperature and pressure, the flow at the minimum cross-sectional area of the choked convergent divergent nozzle should be equal to 1. So for subsonic flow, this acts as a nozzle, and for supersonic flow, the diffuser acts as nozzle. Converging diverging part. Sorry, diverging section acts as a nozzle for the supersonic flow. So the answer to this problem is sonic. Flow should be sonic at the choked convergent choked minimum minimum cross-sectional area, that is the throat area. Choose the correct area Mach number relation for varying duct from the following, where V equal to velocity, dV is equal to change in velocity, A equal to area of the duct, dA equal to change in area, and M equal to Mach number. So what will be the equation for the change in area, differential area, to the change in velocity? So the options 1 and 2 are same. Sorry, 1 and 3 are same. So the answer to this problem is dA by A is equal to m squared minus 1 into dV by V. So the change in area can be written as Mach number squared minus 1 into dV by V. In the case of a scramjet engine, air enters from the intake at dash speed and encounters combustion at dash speed in the combustion chamber. So the given question is that of a scramjet engine. So in one of the previous questions, we have seen the example of a ramjet engine. So scramjet engine is the example. is similar to that of a ramjet engine, but it's a supersonic case. So the answer to this problem is the intake as well as the combustion happens at supersonic speeds. So the inlet will be happening. The inlet intake to the engine will be at a supersonic speeds greater than Mach number greater than 1. So the converging nozzle section will be acting as a diffuser. So the converging part will be acting as a diffuser. So the pressure increases within this section. So increase in pressure, it will be doing the similar function as that of the compressor without any moving part due to the formation of shock waves. Then at a higher pressure, at the throat section, the Mach number will still be greater than 1. Here at the inlet, it will be Mach number will be very much greater than 1. Since the Mach number is greater than 1 at the combustion chamber also, the pressure generated after combustion ensures that the Mach number will be greater than 1, and this diverging section will be acting as a nozzle since the Mach number greater than 1. So at the exit will be at a Mach number very much greater than 1. And this will ensure that the engine produces greater thrust power. So in the case of aircraft engine, we require high thrust power. That means higher kinetic energy at the exit of the engine. So if it was a power producing engine or a electric power generation plant, we would have required this Mach number should be very much less than 1, so that almost all the kinetic energy is converted into the so we would be having a diffuser at the exit rather than a nozzle. So all the kinetic energy will be converted to the power produced by the power plant. But in the case of engine, it is reverse. We need maximum velocity at the exit. So that's so in the case of a scramjet engine, the only difference with that of a ramjet engine will be that at the combustion chamber or the throat, Mach number will be less than 1 in the case of ramjet engine, and it will be greater than 1 in the case of scramjet engine. So everywhere in the scramjet engine, the speed will be supersonic. So supersonic at the inlet and supersonic at the combustion chamber, as well as supersonic at the exit. Select the correct sentence from the following. The flow velocity along the length of the duct increases for the supersonic inlet through the converging duct. The flow pressure along the length of the duct increases for the subsonic inlet through the diverging duct. Flow velocity along the length of the duct decreases for the subsonic inlet through the converging duct. So the fluid pressure along the length of the duct increases for the supersonic inlet through the diverging duct. So what will be the correct answer? So the answer to this problem is the fluid pressure along the length of the duct increases for the supersonic, increases for the subsonic inlet through the diverging duct. So the option is B. For a subsonic inlet. So this is the diverging duct, and for subsonic inlet, that is Mach number less than 1, along the section area increases. So the formula is formula relating area change in area and the velocity is dA by A is equal to m squared minus 1 into dB by V. So for a Mach number less than 1, the quantity will be negative. So the relationship between A and B will be inverse. So once the area increases, velocity decreases. So this diverging set will be acting as a diverging duct will be acting as a diffuser for a subsonic flow. That implies the velocity decreases. Mach number will reduce less than 1. So as velocity increases, pressure increases. For therefore, the fluid pressure along the duct, along the length of the duct increases for subsonic flow through a divert. So the flow is subsonic and the duct is a diverging one, and hence the fluid pressure increases. So this is the option. This is the right option. So for a converging duct, for subsonic flow, Mach number less than 1, it acts as a nozzle. So similar equation, Mach number less than 1, as area decreases, velocity increases. Correspondingly, pressure decreases. So for a converging duct, for a subsonic flow, the velocity increases. So this option is wrong, and pressure decreases. And similar analysis for a converging duct for Mach number greater than 1 from this equation. So as area decreases, velocity decreases, but pressure increases. So the converging section will be acting as a diffuser. So for a supersonic inlet, for a converging duct will be acting as a diffuser where the pressure increases and the velocity decreases. So this option is wrong. And the last one for a diverging section, Mach number very much greater than 1, for area increases, velocity increases, and pressure decreases. For a supersonic inlet through a diverging section, velocity increases and pressure decreases. So this option is also wrong. So the only option right is the second option. So the question is regarding the function of an intake of the aircraft engine. It is to increase the kinetic head of air, increase the pressure head of air at the entry of the exit and entry of the engine, reduce heat losses, increase turbine work output. So what will be the function of intake of the aircraft engine? It's more like a diffuser. For a supersonic inlet, that will be a converging section. For a subsonic engine, it will be a diverging section, and that will be increasing the pressure head of the air at the entry of the engine to avoid the use of to provide air at a higher pressure to the combustion chamber. So the function of intake is to increase the pressure head of air at the entry of the engine. For the supersonic flow through the nozzle, the pressure and velocity dash while flowing through it. The nozzle for a supersonic flow, diverging set duct will be acting as a nozzle. So in the nozzle, velocity increases and pressure decreases. So the pressure decreases and velocity increases. So the answer is 3. Which one is correct for the fluid flow through the diverging passage? Always behaves as a diffuser? No. Depending upon the Mach number, the diverging pass will be acting as a converging or a diverging section. Always behaves as a nozzle if the inlet flow is subsonic. If the inlet flow is subsonic, if the inlet flow is subsonic, so for Mach number less than 1, so this decreases. This also negative, so velocity increases. For a subsonic flow, I beg your pardon, area increases. So the velocity decreases. So the subsonic flow, the diverging section will be acting as a diffuser. So this is also wrong. Only acts as a diffuser if the inlet flow is supersonic. If the inlet flow is supersonic, this diverging section will be acting as a nozzle. So this is also wrong. It acts as both a nozzle or a diffuser, but depends upon the inlet Mach number. So that is the right option. For incompressible flow through a diffuser, pressure always increases, but velocity remains a constant. Pressure decreases when the inlet flow is supersonic. Velocity always decreases and pressure increases. Velocity increases when the inlet flow is subsonic. Given case is a diffuser. So for a Mach number less than 1, diverging set act as a diffuser. For Mach number greater than 1, the converging set act as a diffuser. So the function of a diffuser is to increase the pressure and decrease the velocity. So in this case, pressure always increases, but velocity, pressure always. The pressure always increases and the velocity always decreases. So for diffuser, function of a diffuser is to increase the pressure and decrease the velocity. So a diverging duct will be acting as a diffuser for a subsonic flow, and a converging duct will be acting as a diffuser for a supersonic flow. Okay. The purpose of any aircraft gas turbine inlet is to provide sufficient air to the compressor to have minimum drag force, reduction in velocity, all of the above. What is the use of inlet? So the inlet will be acting as a diffuser where it increases the pressure and decreases the velocity of the incoming air. So reduction in velocity and increase in pressure, and also to provide sufficient air supply to the compressor, and also the inlet area should be sufficiently small to have minimum drag force. So the purpose of an aircraft gas turbine inlet is to provide all of the above. So the answer is D, 4, option 4. Because of the diffusion in the inlet casing, air velocity decreases and pressure increases. Air velocity and pressure decreases, air velocity and pressure increases, air velocity increases and pressure decreases. So we have seen in the previous problem, the diffusion in the inlet casing will be increasing the pressure and decreasing the velocity. The function of an exhaust nozzle in the case of a aircraft engine is to decelerate the flow, allow for cooling of the walls, increase jet noise, none of the above. So the function of the exhaust nozzle is to allow for cooling of the walls. The exhaust nozzle increase the flow velocity. So this option is wrong. It decreases the jet noise. And it allow for the cooling of walls. So the answer is option B. Supersonic aircraft are provided with convergent nozzle, divergent nozzle, convergent divergent nozzle, none of the above. We have seen in the previous analysis for a ramjet or a scramjet. For a scramjet engine, inlet will be Mach number greater than 1. This converging set will be acting as a diffuser, and it reaches a combustion chamber. Mach number will be still greater than 1. The diverging set will be acting as a nozzle. So supersonic aircraft has got Mach number very much greater than 1 at the exit, providing higher thrust power. So it acts as a convergent divergent nozzle. Subsonic aircraft are provided with convergent nozzle, divergent nozzle, convergent divergent nozzle, none of the above. In the case of subsonic aircraft, the Mach number at the exit will be still less than 1. So Mach number at the inlet will be very much less than 1. In order to increase Mach number, the converging duct need to be provided. This converging duct will be acting as a nozzle for Mach number less than 1. So still the exit will be less than 1. So there is no question of Mach number going above 1. So because of that, The whole aircraft engine is being provided with a convergent nozzle. Okay. So that completes the problem solving session for this week. So we have seen a few numericals based on the free vortex type problems. And we calculated the degree of reaction of a reaction turbine in terms of the blade angles. And we have seen a few multiple choice questions based on the nozzle diffuser section of the aircraft engines. And that completes the topic for this problem solving session, as well as that is the end of the lectures. And in the next week, we will be having a revision on the topics that we have covered in the previous 11 weeks. And we will have, and that will be helping you to solve the exam problems, as well as the coming assignment problems as well. So we will meet the next week at the same time from 7 to 9, and that will be completing the lecture. Thank you.